Welcome to this explainer. Today we're diving into a really cool grade 8 geometry concept, solving right triangles. Honestly, think of a triangle with missing sides and angles as a bit of a mystery, a mathematical case just waiting to be cracked. I mean, have you ever wondered how engineers figure out the exact height of a massive skyscraper without dragging a giant tape measure all the way up? Or how navigators pinpoint the exact distance to a ship way out on the horizon? Well, spoiler alert, they don't guess. They use a very specific, highly specialized math toolkit. And today, we're going to look at how we can use those exact same properties to unlock literally every single missing dimension of a right triangle.
Here's our quick roadmap for today. We'll start with the right triangle toolkit, then move on to solving for missing sides, followed by solving for missing angles. After that, checking for reasonableness, and finally, a recap and transfer question.
All right, Section 1, the right triangle toolkit. Let's gather up the fundamental geometric tools we're going to need before we do any heavy lifting.
Okay, so the very first item in our toolkit is an absolute classic. You probably know it, SOHCAHTOA. It's a handy little memory device for our primary trigonometric ratios, sine, cosine, and tangent. But why do we actually care about these? Well, these ratios are basically the master keys that unlock the relationship between the angles we can see and the side lengths we can actually measure. It breaks down perfectly. SO stands for sine equals opposite over hypotenuse. CA tells us cosine equals adjacent over hypotenuse, and TOA means tangent equals opposite over adjacent. Just by keeping these three simple ratios in your back pocket, you can completely connect the dots between degrees and distances.
Now, what's really fascinating here, and you can kind of see it with these eye icons on screen, is how the opposite side and adjacent side shift. It depends entirely on the perspective of the acute angle you're looking from. The hypotenuse? That's your one constant. It is always the longest side directly across from that 90-degree right angle. But the adjacent side is just the leg sitting right next to your chosen angle, while the opposite side is the leg all the way on the other side of the triangle. So if you change your viewing angle, boom, your adjacent and opposite sides instantly swap roles. It's literally all about perspective.
Moving right along, the next tool in our kit is the legendary Pythagorean theorem. It states that for literally any right triangle, the square of the hypotenuse, which we always label C, is exactly equal to the sum of the squares of the other two legs, A and B. You know the drill. A squared plus B squared equals C squared. If you happen to already know two side lengths of a right triangle, this powerful little formula is hands down the fastest way to calculate that third one. Just remember one golden rule we'll definitely need later. C must absolutely always be the longest side of the triangle. No exceptions.
And rounding out our toolkit, we have the angle sum rule. This is just an undeniable geometric fact. The interior angles in every single triangle out there will always sum to exactly 180 degrees. Honestly, this rule is a massive time saver. It rescues us from doing a bunch of complicated algebra when we really don't have to. Think about it. In a right triangle, we already know one angle is exactly 90 degrees, right? That means the other two acute angles are complementary. They just have to add up to the remaining 90 degrees to hit that magic 180 total. Easy.
Which brings us to Section 2, solving for missing sides. Let's see what happens when we actually put this toolkit to work.
So here is our master blueprint for fully solving a right triangle. Don't think of this as a boring list of chores. It's more like a logical chain reaction where every single step perfectly sets up the next. Step 1. Identify your given angle and side measures. Basically, you figure out what clues you already have to work with. That leads right into Step 2. Set up a trig ratio, using our good friend SOHCAHTOA to crack the code and find your first missing side. Now that you've got two sides, you trigger Step 3. Rely on the Pythagorean theorem to find the third side. And finally, Step 4. With your sides fully complete, just use that angle sum rule to easily snag the last missing angle. It perfectly weaves together our algebraic and geometric tools.
Let's actually put this chain reaction into practice, shall we? I want you to pause the explainer right here, maybe grab a pencil, and test your toolkit. If we know the length of the opposite side from our angle, and we want to find the hypotenuse, which trigonometric ratio connects them? Take a quick second and think about it. Got it? Well, the crucial hint is right there in the SOH part of SOHCAHTOA. It immediately tells us to use the sine ratio. Since sine equals opposite over hypotenuse, we just plug in our known opposite side length and our known angle degree right into the equation. From there, it's really just basic algebra. You just multiply or divide to isolate the unknown variable for the hypotenuse, and bam, just like that, you found your missing side.
Okay, let's keep this momentum going. Section 3, solving for missing angles.
Time to hunt down that final angle.
All right, time for our second pause check. Go ahead and freeze this explainer for a moment and see if you can figure this out using that angle sum tool we discussed earlier. If our right triangle obviously has a 90-degree angle and our given acute angle is 30 degrees, what's the exact measure of the third final angle?
Yep, as you can see perfectly illustrated here, that final angle absolutely has to be 60 degrees. This is just a brilliant example of the angle sum rule in action. We take the total 180 degrees that every triangle is forced to have, subtract the 90-degree right angle, subtract the 30-degree acute angle, and we're left with a nice 60-degree slice. See? No complex trigonometry needed for this step, just some simple, elegant deduction.
Section 4, checking for reasonableness. Because getting a number is one thing, but making sure it makes sense is another.
So we have all our missing numbers, but our job isn't quite finished. Just getting a number on your calculator screen isn't enough. We have to verify if our answers actually make logical sense in the real world. Take a look at the calculated measures on the left here and compare them to our reasonableness rules on the right. First things first, always check your units. If the problem is in feet, your side length's got to be in feet, not inches, and definitely not degrees. Next up, check your hypotenuse. If you calculated a hypotenuse of, say, 14 feet, but one of your legs is 20 feet, yeah, you know you've made a math error somewhere. Because the hypotenuse absolutely must be greater than sides A and B. It's the longest side. Finally, just do a quick mental check to ensure all three angles perfectly sum to exactly 180 degrees.
And finally, Section 5, recap and transfer question. Let's lock in everything we've learned and test those skills.
Seriously, excellent work today. Just look at how far you've come, from just guessing at missing dimensions to confidently executing a full-blown mathematical strategy. By strategically combining these tools, you're virtually unstoppable. You can use your trig ratios to track down those tricky missing sides. You can seamlessly apply the Pythagorean theorem to find a third side the exact second you have two. You can lean on that 180-degree angle sum rule to instantly lock down missing angles without even breaking a sweat. And most importantly, you now have the discipline to step back and check your side lengths and units for absolute reasonableness. You truly have the power to unlock every single dimension of a right triangle.
Now, I'm going to leave you with this final transfer question to really test your skills in a real-world scenario. Imagine a telephone pole that casts a huge 50-foot shadow. Obviously, you can't just climb it to measure its height, but right nearby, an 8-foot-tall traffic sign casts a 10-foot shadow. Because the sun hits them at the exact same angle, these actually form similar right triangles. So how can you use proportional relationships between these similar triangles to indirectly measure the exact height of that telephone pole? Think about how the ratios of their corresponding sides must be equal. If you can unlock the relationship between those shadows, you unlock the ability to measure mountains, skyscrapers, or even the distance to the stars using just the ground beneath your feet. Thanks for joining me on this explainer, and hey, happy calculating!